making a request. And that way we'll keep the state, we'll keep the session variables, but we won't have to hold on to them. So if you control part or all of that, you have an encryption oracle. So for instance, the view state in ASP.NET is frequently a partial encryption oracle. Now, its usefulness is somewhat limited in that the key being used is only used for several other things inside ASP.NET. But I have seen people who just want to use one key for everything and will actually go to great lengths to use the machine key as the same key for encryption. So another frequently encrypted piece of data is passwords. Financial data is also frequently encrypted. Anything sensitive is often subject to encryption. So trying to modify these things and then look for any of those encrypted pieces of data changing is a good idea. But being encrypted is not enough. We also need to be able to manipulate it. So here's an example of where you might find an encryption oracle. Let's say that you have an authentication cookie. So this is a situation where you have session data that you want to store on the client, with the client encrypted, and not store as session variables and hold down the server. So consider an authentication cookie that's the username concatenated with a colon, password hash, colon, and a timestamp. So we can't do any sort of replay attacks because of the timestamp. And we'll assume that the usernames can't include a colon character, so we don't have delimiter injection, no field injection stuff. But this does mean that we have a partial encryption oracle. We can't control the whole thing, but we control the username. If the only restriction is that we can't control the colon, then we can do a lot of interesting things. We can encrypt a lot, except we just can't control what goes at the end of it. Now, there are definitely ways to get around this. Does anyone know what null byte injection is? Poison null byte. Okay, so we've got some. The poison null byte is an issue where the null byte, hex 0, is seen as some frameworks, seen by some frameworks as just another character, and in others it's a string delimiter. So for instance, when you're doing file inclusion attacks, if you're tacking .htm onto the end of everything and thinking, well, this is fine, this is no problem, everything's good here, they can only include HTML files, you put a null byte on there. And most web application frameworks will see that as just another character, but once it gets passed back to the file system, pretty much every operating system is going to truncate at the null byte because they're C-based, and the C is a language in which the null byte is a string terminator, so it cuts off the end. So we can do some similar attacks here. The fact that we can't control the end is actually just fine for a lot of attacks. So that's interesting. So we can register with some username and log in and take a look at that cookie, and we register with the username of whatever it is we want to encrypt. So groovy stuff there. So wanted to mention padding oracles as well. So with a padding oracle, the input has to be encrypted, and it has to be with a padded block cipher. With stream ciphers, you're encrypting 1 byte by 1 byte. So the end of the cipher text, the end of the plain text is just where the text ends, and not where you've put some arbitrary marker. So it also has to be distinguishable when you've passed something in that has valid padding or invalid padding. And this is the essence of a padding oracle. Now, I know that with a padding oracle, you can do all sorts of crazy things, and you can take over an old ASP.NET installation. But really, all a padding oracle allows you to do is to tell whether or not the padding was actually valid. Now, in the case of the cipher block chaining mode, where the ciphertext for each block in a block cipher is used as the initialization vector for the next one, so as to prevent repetitive plain text from producing repetitive ciphertext, to remove any sort of distinguishable patterns that might allow you to see that this is this message and this is that message when they're encrypted. That's actually going to allow you to change the padding bytes and then change the corresponding bytes in the previous block until you get valid decryption again. So until you get to the point where the padding is valid again. So like I said, I don't want to go too much into how padding oracle attacks work, But padding oracles can, in that way, be converted to decryption oracles. Now, the interesting thing is Duong and Rizzo, who presented the padding oracles everywhere presentation, also talked about an attack where you can use this decryption oracle functionality of a padding oracle in this particular type of situation to encrypt data, where you're just changing the data until you get the output that you really want. The way that it works, it might be limited in that the first block is garbled. So if you end up finding a padding oracle and using it as an encryption oracle, you can't control the first block. And again, there are some situations where that's not a problem, but it's something to be aware of. So let's talk a little bit more about exploiting these crypto oracles. So to convert one oracle into another, most of this involves brute forcing. So we talked about padding oracles and using them to decrypt and encrypt data. Decryption oracles can be converted to encryption oracles. And the idea is that you just brute force guess a whole bunch of ciphertext until it decrypts to what you want it to. And that way you have the plain text you want, and your input is really what you're looking for. Now, since block ciphers do this several characters at a time, you need to guess all of the characters in that block at the same time. So you need to keep doing that until you get it right. So that's a little bit more complex, a little bit more heavy on the queries. Whereas if you're talking about a stream cipher, that's one byte at a time. So you can just guess even one bit at a time until you get exactly what you're looking for. So encryption oracles can be converted to decryption oracles in a very similar way. And again, the same difference between the effectiveness when you're talking about stream and block ciphers applies. So we're going to talk about doing a little bit of crypto recon using oracles. So let's say you have an encryption oracle. If you encrypt the same plain text twice and it comes out to the same ciphertext, you know you have the same key, same initialization vector, and a deterministic cipher being used to encrypt the data. So if the ciphertexts are identical, you know all of these things are true. You can also check for stream versus block ciphers. This is pretty easy to tell. So you can encrypt some piece of plain text, and if the size is dependent on the size of the plain text divided by 8 or 16 or something like that, then it's a block cipher. And if it just grows and with the plain text, no matter how many bytes you're tacking onto the end of it, linear relationship, you have a stream cipher. You can also check for ECB block mode. So this is a little bit different from CBC, which I described earlier, in that each block is independent of other blocks and are encrypted independently. So if you have repetitive plain text like 8 uppercase A's, 8 uppercase B's, 8 uppercase A's, 8 uppercase B's, and that's your plain text, your ciphertext is going to have blocks 1 and 3 being identical and blocks 2 and 4 being identical. So you can see those patterns. So you can try to show that, you can try to guess that behavior. You can try to get it to produce that behavior with an encryption oracle. And ECB, you can obviously see how that's a problem, because we can then take those blocks and rearrange them however we like. So we can also check for stream cipher feedback. So when you're working with a stream cipher, sometimes the encryption of some particular bit, whether or not it gets flipped, is dependent on earlier bits in the plain text or the ciphertext. What we can do to check on that is to encrypt some plain text and then modify the beginning of it and see if the rest gets screwed up. So let's talk about using oracles to attack some bad algorithms. So occasionally people try to write their own crypto and it doesn't work out too well. Unless you're a cryptographer, and even then sometimes it doesn't work out so well. So let me show you some real homespun crypto that I've seen in the wild during a pen test. So here's a plain text, hello, and its corresponding ciphertext, which is a bunch of what looks like gibberish. So I found an SQL injection flaw, but it did not allow me to do anything but read data from the database. So I said, okay, well, I'll get all the credentials from the database. Turns out the passwords were all encrypted. And it was this bizarre looking stuff that doesn't really look like strong crypto. And so I thought, okay, well, let's play with this. So the first thing, I want to know if there's substitution. Are we switching characters for others? And that's definitely true, but if we put in 4 uppercase A's, we can see, there are no uppercase A's in that. There is definitely substitution here. We can already start to see patterns in this as well. The plain text is repetitive, the ciphertext is repetitive as well. So the next thing we're looking for is if there's transposition, if characters are being switched around before or after the substitution occurs. So we'll submit AABB, and we see something similar to what we saw last time, and you can already start to see patterns in this very, very quickly. So there doesn't seem to be any transposition, and we can see more patterns. The K also seems to be a delimiter. So one thing that you'll notice if you look at this, there are a couple different. You can have different lengths with these characters. So the K is just standing in to separate characters so that even with variable lengths for the ciphertext version of different characters, anywho, let's move on. So it also doesn't seem to change on position. So next thing we do is we submit a variation on the last pattern, and we notice that some more of our assumptions are proving to be true. That like this ABE is uppercase B and LO is A. So this is pretty much exactly what we expected. The substitution doesn't seem to change no matter where the character is in the plain text. So next thing we'll do is just submit every character, and we get back the entire key. So we see what every character is substituted to. So this is a trivially weak cipher, and the Oracle has helped us just totally destroy this cipher. So more bad algorithm stuff. Some people use XOR to encrypt data. And the funny thing about XOR is that it has this weird property. So if we use an XOR operation between a plain text and its corresponding ciphertext, we get the key. So that's ugly, and you really don't want to be using XOR. So another thing about XOR, for some simple ciphers like XOR, the encryption routine is the decryption routine. Thus, an encryption oracle is also a decryption oracle, which means that I can encrypt or decrypt any data that you're using, which essentially means that this encryption is totally useless as soon as an encryption oracle is introduced, and even before that, actually. So please don't use XOR. So now I'm going to do a demonstration. We're going to take a look at the default encryption algorithm in Cold Fusion, the CFMX compat algorithm. Now, I did a little bit of Googling on this and found that everyone said, hey, don't use this algorithm, this is weak. Adobe says this is the weakest cipher that we have, but for some reason they make it the default one that you use. So, okay. So I have whoops. What? Oh, hey. Thanks, guys.